Hi everyone, welcome back. This is the final section of today's lecture. We're going to be talking about linear first-order ODEs and integrating factors. So I'm going to apologize a little bit in advance. This is going to be a pretty math-heavy section of the course, and we're not going to give examples until next week. But we're not going to be as math-heavy as an ODE class, and the first thing I'm going to mention is this really important theorem, which we are not going to prove. So if you have a first-order linear ODE initial value problem, if your p of x and q of x are continuous functions on some interval of the real line containing your initial value x naught, then there exists a unique solution to the initial value problem for every point in I. So basically, this is just saying there exists a solution, and it is unique if you specify the initial condition. So now, in a more theoretical ordinary differential equations class, you spend a whole lot of time proving various existence theorems, various uniqueness theorems, and also existence uniqueness theorems like the one we have here. Luckily for you all, we're not going to do that. We're just going to assume that any problem I give you is going to have a solution, and also assume that any problem you encounter in real life, in biology, is also probably going to have a solution, because if it didn't have a solution, then it wouldn't be something you were trying to model. This is not true in general in mathematics, but luckily this turns out to be good enough for most mathematical biology, as well as a large number of problems in physics, though in physics you start running into some more of the edge cases. Okay, so we're not going to spend too much time on that. Just be aware that these things exist. But I will have to introduce a little bit more mathematical formalism. So we've been talking about these dx's and dy's, and see these are the intuitions behind the notation dy by dx when you're taking derivatives, and they can be thought of as infinitesimally tiny changes along the x or y axis. And let's go ahead and give an example of this just to remind you all. So our quick example is that if you have y prime is equal to x squared, you can split this into dx over dy, x squared, dy is equal to x squared dx, integrate both sides, and you get y is equal to 1/3 x cubed plus c. And so then if you let f of x be equal to 1/3 x cubed, one other thing you can say is that d of f of x, so this is something called the differential operator, is going to be d of 1/3 x cubed, and so then you have df is equal to x squared dx. Okay, and you can sort of see that this is basically analogous to multiplying by the dx in the other version of the equation. Okay, so we have these ideas of differentials, which are infinitesimal changes of some variable along some direction. It turns out that you can have these same sorts of ideas for multivariable functions. And this is the reason why when we talk about partial derivatives, you still use the similar like curly t notation. So if you have a function of both z is equal to f of xy, a function of both x and y, then you recall, oh, can you go over that again? Yes. So I'm going to go over it about 3 times. So if you still have questions afterwards, I will ask me again then. So basically, you can think of the differential as a tiny change of some variable in some direction, right? So that's the whole idea behind derivatives, because you're doing a tiny change in y compared to a tiny change in x. But now, if you have multivariable functions, you can also think of a tiny change in f divided by a tiny change in x. And that gives you a partial derivative in the x direction. So things like df dx is a partial derivative in the so this is tiny change in f. Oh, can you see that? Will I go? Oh yeah, you can see that. And this here is a tiny change in x. Okay, so you can think of it similarly with partial derivatives, so you have to be a bit more careful because you have to hold the other variables constant. And so one of the things we discussed when we were talking about partial derivatives and multivariable functions is that we had some gradient vector that gives the partial derivative in any particular direction. So if you have your gradient vector, you can take the dot product of your gradient and some direction vector, u equal to u sub x, u sub y, and that gives you the direction that gives you the partial derivative in that direction. This is a little bit complicated. A lot of what I'm going to talk to you about today is just going to be justifying a solution if you don't fully understand it, that's not great, but it's all right, because I won't be expecting you to understand all of the rigorous theory that I'm introducing. I'm just trying to give you some intuition for why a result I'm going to show you later is true. Actually, let me jump ahead to it, just so that you guys don't get too scared. So basically, at the end of the day, I'm going to give you a really long, ugly algorithm for solving a first-order ODE. Right now, I'm justifying why we can do this. Okay? So don't worry if not all of this makes perfect sense yet. But anyway, coming back to this, we have some derivative in a particular direction, and we can define the total differential of a multivariable function z by taking these partial derivatives, because this is the change in the of z as you go in the direction dx by dy. So a tiny change in some other direction where this is the gradient. Okay, so this is a lot more advanced. I'm just giving you some intuition for why this is true. So you can define this total differential by taking a partial derivative of your function f with respect to x, multiplying by dx, taking a partial derivative of f, and by del y, and multiplying it by dy. We won't have time to go over this rigorously, but I will give you some examples, which should hopefully make a lot more sense. So let's start with some examples and how to actually compute these. So if you have z is equal to x squared plus 2xy plus y to the fourth, then dz is going to be equal to, you take the partial derivative with respect to x. So that's going to be 2x plus 2y times dx. Take the partial derivative with respect to y. So that's going to be 2x plus 4y cubed dy. And so now that is the total differential of dz. If you want to, you can also expand it out. It doesn't really matter. So this is 2x dx plus 2y dx plus 2x dy plus 4y squared dy. But often it's useful to combine together all the dy's and the dx's. So let's give a couple more examples, just to let you see what's going on. So we have f of xy is equal to sine of 2x plus y squared e to the x. So the total differential, there's a question about what exactly is it. The total differential you can think of as a tiny change in the function f, given tiny changes in x and y. So given some tiny change in x and y, what is the tiny change you get in z? Okay, you can think of it sort of like a partial derivative, but it's not exactly the same thing. And there's a reason we're going through this interlude. But to calculate it, all you have to do is take partial derivatives. So df here is going to be equal to 2 times cosine 2x dx plus y squared e to the x dx plus 2y e to the x dy. And let me do one more, and then we'll go through it a little bit more slowly, which is if you had z is equal to x squared y squared, then dz would be equal to the partial derivative, and so this is what I'm doing this entire time, the partial derivative with respect to x of x squared y squared times dx plus the partial derivative with respect to y of x squared y squared times dy. So this is going to be equal to 2xy squared dx plus 2x squared y dy. Okay, let's try it out. So remember, all we're doing here is we're taking partial derivatives and multiplying by dx and multiplying by dy. So for this function, which of these is the total differential of f? So remember, what you're doing here is you're taking df is equal to the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Okay, so we started getting a couple answers. We got A. So let's see what happens. So we have this is equal to the partial derivative with respect to x is going to be 2x plus e to the y cosine x times dx plus, well, what's the partial with respect to y? Let's just e to the y sine x dy. So it is indeed A. Looks like we got some C's as well. So you have to be a little bit careful when you're taking these partial derivatives, that you need to make sure to take the partial derivative over the entire thing. Okay, so let's try it one more time. So let's try z is equal to 5x squared over y minus 1 plus 1. So what is the partial derivative of this thing? So again, what you're doing is you're taking dz is going to be equal to the partial derivative of z with respect to x times dx plus the partial derivative of z with respect to y times dy. So since we're running a little bit low on time, I'm going to go ahead and start writing this out, but you should continue working on it. Oh, looks like we've got a couple, we started getting some replies. So we got one C, we got one D, and let's see, we got B or C in some cases. Okay, it looks like C is the majority answer. My guess is that some people made minor arithmetic mistakes, which is a fairly common thing to happen. This is why early on in this course I said you guys need to have your integrals and derivatives really down pat, because you're going to be doing a lot of these. So let's see what happens. So this dz is going to be equal to dz dx. Well, that's not going to do very much. That's just going to be 10x over y minus 1, because you set y constant times dx. And this other one is slightly uglier. So you have 5x squared over, well, y minus 1, that's y minus 1 to the negative 1 power. So this is going to be y minus 1 squared, and you have a negative sign because it was minus 1 power times dy. And so this here is equal to, let's see, 10x. So you have the minus sign, and so it's actually going to be equal to b. Unless I did something really wrong, since it looks like everyone else is getting answers that are slightly different. So let's see, 1 over y minus 1, so that's y minus 1 minus 1, minus 1 over y minus 1 squared. So that's minus 5x squared. Oh, no, it's not b, it's d, because I just looked at them wrong. Sorry, so that's d here, because you have the y minus 1 squared, and minus 5x squared. Okay. Yeah, sorry about that. Arithmetic errors are unfortunately a commonplace thing, and you need to watch out for them. Okay, but so that's the rough process for computing this total differential. And can you just break down how to do the second partial derivative? Oh, yeah, sure. So let me do that, because we want to all be on the same page. So if you have dy of 5x squared over y minus 1, that's going to be equal to the x you can treat as constant, so that's 5x squared dy of... Oh, wait a moment. Did I do this wrong? I think I may have done this wrong. No, I did it right. Okay. So you're taking the derivative, right? So you're taking the derivative of this, so that's equal to 5x squared times the derivative of y minus 1 to the minus 1 power. So that's equal to 5x squared times minus 1 times y minus 1 to the minus 2 power. And so that's why you get minus 5x squared over y minus 1 squared. Okay, so let's move on. For always, be really careful about arithmetic mistakes. They'll be common. We'll take off some points for it. You'll get partial credit even if you do it, of course. So now, what is an exact differential? A differential, so if you start with something that looks like dz is equal to p of xy dx plus dq xy, it's an exact differential if there exists some function such that the total differential is equal to to see that the total differential is equal to that's the total differential of some function. Okay, so this is just going backwards. So if it happens to be the total differential of some function, then it is an exact differential. And one other nice fact we know is that d squared f dy dx del x is equal to del squared f del x del y for most nice functions. And so therefore, a quick way to see if a differential is exact is to check if del p del y is equal to del q del x, precisely because this here is just del y of del f del x, and this here is del x of del f del y. Let me give a couple of examples. So in the first example, note that this is what we computed as the total differential. So this should be an exact differential. Del z is equal to 10x over y minus 1 dx minus 5x squared over y minus 1 squared del dy. And so here, what we have here is this here is going to be our p of xy, and this here is going to be our q of xy. And you'll note that del p del y is going to be equal to minus 10x over y minus 1 squared. And del q del y is also equal to minus 10x over y minus 1 squared. And therefore, this is exact. So that's a quick check to see if it's exact, even without knowing what function you originally started with. And if you have del z is equal to, say, 5x squared plus 1 dx plus xy squared del y, dy, this here is p of xy, and this here is q of xy. You'll note that del p del y is equal to 0, and del q del x is equal to y squared. So this is not exact. And it turns out that if you have an exact differential equation, that's something you can solve. And it's a little bit complicated, but what you do is you basically take advantage of the fact that you know that it's a total differential. So if you started with something like dy dx is equal to minus 2xy over x squared plus 1, well, you might try to multiply this out and try to see if it's separable. Unfortunately, it's not easily separable. Let's see. Is it separable? It is actually separable, but let's not try to solve it that way. So you have x squared plus 1 dy is equal to minus 2xy dx. And if you rearrange those, this is 2xy dx plus x squared plus 1 dy is equal to 0. And you note that this here is p of xy, and this here is q of xy. And we can check to see if it's exact. So del p del y is equal to 2x, and del q del x is also equal to 2x, and so this is exact. And because this is exact, what you can do is you can take the integral of x squared plus 1 dy is equal to x squared y plus c of x. So what we're trying to do now is we're trying to figure out what the actual function f was. An integral of 2xy dx is equal to x squared y plus c of y. This is somewhat complicated. I don't expect you to be able to do this immediately. We'll go over it again if we end up needing it. And so what you can do is you can guess, based off of these two partial integrals, that f of xy is equal to x squared y plus y. And you can check. If you take the total differential of this is equal to 2xy dx plus x squared plus 1 dy. So basically what we did there is we found a particular function f of xy such that the total differential is the left-hand side of our function. And so then, therefore, you can just take the integral df, which is equal to, and you know integral of f is df is equal to f plus c. This implies that this entire equation, if you take the integral on both sides, is x squared y plus c is equal to 0, which implies that y is equal to c over x squared plus 1. Now, you can also double check that this is actually the right answer, and the way you do that is you just plug it back in. And when you plug this back in, what you get is that dy dx is equal to minus 2xc over x squared plus 1 squared, which happens to be equal to minus 2xy over x squared plus 1, so this does work. Okay, so basically, if it's an exact differential, then you can take the integral of an entire weird side. So basically, yes, so you can sort of ignore this part for now and just go straight to this guess. So we know that it's exact, and so we know there exists some function. And the two integrals I did up there were just so we could figure out what that function was. And so you know it's a function that when you take the integral with respect to y, and then when you take the integral with respect to x, you get a particular thing. And you have to get the same thing. And so your guess here was that this is x squared y plus y. How we do that exactly doesn't really matter for the purposes of this lecture, just that you can do it. There's some way of guessing your f of xy, and once you guess the f of xy, you note that df is equal to this entire thing, right? But this box here is precisely this box. And therefore, you know that df is equal to 0, right? And so here what you have is the integral of df is equal to the integral of 0. And so therefore, you get the f plus c is equal to 0. But f there, what we knew was x squared y plus y. And so therefore, you get y is equal to c over x squared plus 1. Okay, so that was a little bit fast. And I am going to go a little bit quickly to go through this. What's going to be important is the formula we could come up with at the end. And I'm just basically giving you some general tools that we use to derive this formula. There are also tools that are useful in their own right, but we won't. I'll go over it again if we need it. So now, sometimes we can find something called an integrating factor to. You know what? We are out of time, and I'm not going to be able to do this material justice. Let me go over this material again next Wednesday, because I would be rushing through the remainder of this lecture. So we only have 3 minutes left anyway. Let me just go give you a brief preview of what we'll be doing, and then we'll go over all this a little bit more slowly on Wednesday, since my guess is that I'm going relatively quickly for many people, and this is a very mathy lecture. Next Wednesday will also be chapter 8, so we'll be continuing. So next Wednesday, so really this Wednesday and next Wednesday are all 1 week, because it just so happened to be broken up by Canada Day and the U of T presidential holiday. So next Wednesday will be the same material, just different ordinary differential equations. But let me just go ahead and give you a quick preview of everything, which is that it turns out that every first order ODE can be turned into an exact differential using an integrating factor, but unfortunately there's no way of systematically guessing. And so we will not expect you to use integrating factors outside of a few special cases where we know the integrating factors. And it turns out that there is an integrating factor that we know for all first order ODEs. And we can do this manually. And this gives you a general solution, which is that for a first order ODE, we know what the integrating factor is, and so we can do that entire procedure, or you can just memorize this equation at the end. So you won't in general be able to guess the integrating factor, and I will give you, unless it is in a very specific form. But luckily, for the first order ODEs, it's in a form where we know what the integrating factor is. So we know what the integrating factor is for a first order ODE, and so this gives you a step-by-step algorithm for solving a linear first order ODE by using this integrating factor technique. We'll go through it again next Wednesday because I have unfortunately run out of time. But what this means is that for first order linear ODEs, you can always solve it by going through this entire procedure. And if you want to write it down one ugly equation, it's this thing here. Though I certainly never memorized this. I just follow the procedure here, since This is a general procedure that we're applying to this first order ODE. And with that, I apologize for running, or for not having finished this part of lecture. I will cover it again next Wednesday, and hopefully it'll be a little bit more clear then. And with that, I will go ahead and end this video. Yeah, so I will see you next Wednesday, and happy Canada Day, and happy U of T presidential holiday.